Hi, physics. I wanted to talk to you about our new stuff, which is visualizing vectors and forces. So in this section, we're talking about forces and how we can look at them just like on paper. So we'll be probably doing some drawing in this section of the class, so not anything too bad. So we're going to be learning about vectors, what they are. We're going to be learning about forces, visualizing these forces, as well as calculating the overall movement and actions of objects because of said forces. Okay? So on we go. To understand vectors and forces, we need to keep these following things in mind. Okay? We need to know that we have a fixed point of reference that we need to look at and understand where, like, so when we look at a fixed point of reference, it's best to look at just the fixed point of reference so that it gives us a concrete place on where to look at our problem from and see what is happening. Okay. And then we also need to understand the magnitude and direction of forces that are in our system. Okay. If those two things don't make sense right now, don't worry, we'll take a look at those. So let's talk about frame of reference right now. So the frame of reference is a point at which the forces are viewed at. Okay. So an example that I would like to give you is if you're driving in a car. If you are driving in your car and you are driving toward another object, say you're driving toward a stoplight, from your point of view, what is moving? You, or is the world around you moving? So many of you would probably say that the world is moving, and many of you would probably say that you are moving, because after all, you're in a car and you know that it moves. But if you looked at, say, if you just videotaped yourself in the car going toward the stoplight, what would you see? Would you see the stoplight moving toward you, or are you seeing yourself moving forward? So the second one, you seeing yourself move doesn't make sense because you cannot see yourself move, because that would imply that you are looking at yourself from a third point advantage. So you can only see things from first person, which means that you see the world move around you while you are stationary, even if you say that you're moving. Whereas if you were looking at your car coming toward the stop sign, say from a camera, the camera or the stoplight camera would see you moving toward it. So depending on your frame of reference, things look different. So here's an example. So let's watch a couple videos here. So here's our first one.
Who are you? You
With
look
wonderful
vaguely
ads, of
familiar.
course. So from this vantage point, is the merry-go-round moving or are you moving? And clearly you would say the merry-go-round is moving. Right? It's moving around. You're not walking around it. And the way you know that is because you have a fixed frame of reference and things around your reference to determine that it is the thing moving and you're not. Right? Like the background itself isn't moving, but things here are. Whereas if we looked at our second video, where we're now in the position of someone on the carousel, would you say that you're moving, or would you say that the world is moving around you? According to your fixed frame of reference, the stuff in the foreground isn't really moving anywhere. Granted, the horses are going up and down, but like everything here is stationary except for the horses moving up and down. However, everything in the background is moving. So who's to say that the world isn't moving around this fixed point of reference? Okay? Alright. So that's frame of reference and talking about it. How you can view things differently based on your point of view and where you are. Okay? So with all of the problems that we're going to be talking about going forward, it's going to be talking about one frame of reference, and that frame of reference only, not from multiple angles, but from the single point of reference. Okay? Alright. Next, we're going to talk about vectors. Vectors look at an object and show the magnitude and the direction of forces that are acting on the object. Vectors are basically just arrows that point in a certain direction and are either big or small to show the magnitude. Okay? They're denoted as F in equations and in diagrams to show you where these forces are, force vectors. Okay? We have several force vectors that we're going to be using today and in this unit. They're listed here. We have F sub g, or Fg, which is the force of gravity. And gravity, we know, pushes downward toward the center of the Earth. Make sure you understand it's the center of the Earth and not the surface of the Earth. It's the center of the Earth. Okay? Then we have F sub n, or Fn, which is the normal force. This is the force of the object on the Earth, or vice versa, where it's the Earth on the object. And we'll talk about that later when we talk about actual forces. We have Fa, which is the applied force. A is applied. This is the force applied to move an object in a certain direction. F of F, or Ff, is the force of friction. This is obviously, we all know what friction is, and it's the force that opposes our applied forces. And then Ft is force of tension. My word got mixed up, so it should be force of tension. If you have something hanging, this is the force of the string or rope holding your object up. Okay, so all of your little letters are self-explanatory because they're listed here. You cannot just write G. You need to put Fg for the force of gravity, because F is referring to, it's a force of, and where that force is coming from. F of G, F of N, F of A, F of F, and F of T are all the force vectors we are going to be using. If you use a force incorrectly, it's not going to be a good thing, because it's going to send the wrong message or be confusing for other people looking at your force diagrams. Okay? So learn these and understand how you use them. And I'll be going through that here with you. So, vectors and FBDs. Okay? FBDs stands for free body diagram. Okay? So, Vectors and FBDs. These forces that we just talked about, like gravity, are all applied to an object in a visual sense to show how they all interact, how all these forces interact, okay? So the visual representation of these vectors is called a free body diagram, or an FBD. It starts with a box, and then the force vectors are added after as arrows. Okay, so in our free body diagrams, we got a box as an object, and we got an arrow to show a force. Okay, arrows can be pointing up, down, left, right, or in any of the angled directions around. Okay, so let's get to using each of our vectors and show you how they are used properly. First of all, let's cover some of Newton's laws as well, so we understand where forces come from and how they are used. So, before we continue, you might be asking yourself what a force is. Forces are a push or pull upon an object resulting from the object's interaction with another object or force. There are 3 laws that focus on motion and forces made by Sir Isaac Newton in the late 1600s. We all know at least one of them. Most of the time it's either the first or the third. Most of the time I hear the third law more often than the first. We're going to go through all 3 of them as we also talk about our force vectors. So here we go. Our first law of motion is an object in motion will remain in motion until another force acts upon it. Okay? This means if we roll a ball, it will keep rolling until something else stops it. In space where there is no opposing forces, it will go forever. However, on Earth, we have other forces that are going to stop the ball, that we can't see. So one of those is obviously going to be like gravity. Other ones are like friction. Things like that will stop it. And those are the something else stopping it to keep it from rolling forever. Okay. The second law of motion is that the amount of force equals mass times acceleration, or F total equals m times a. M, of course, being mass in kilograms, and your acceleration being obviously, in meters per second squared. Okay? All right. So let's visualize an object with gravity affecting it. So this is how we use F of G and how it looks as a free body diagram when there is gravity acting on an object. So as you can see, we have our box as an object, and we have a arrow pointing downward. Obviously, gravity points down toward the center of the Earth. Okay, it always does. And so we always attach our arrows to the center of our boxes. So our F of G, the arrow would just be like so. Okay. All right. If we add a mass to our box, we can actually find out the force of gravity that's holding the box down by using our second law of motion, or the equation F equals ma. So if we calculate that out, we have F of gravity, or the force of gravity that holds it down, is the mass of the box times the acceleration. Acceleration due to gravity is always going to be what we talked about, is 9.8 meters per second squared. That's just what we've calculated it to be. This is a constant, so if you don't have this memorized yet, I would memorize it. Okay, so if we have a 10 kilogram box, that's our mass, and we times it by the acceleration due to gravity, which is 9.8 meters per second squared, we get the force of gravity equals 98 kilograms times meters per second squared. Okay, this is a big mouthful here for units. There's another name for this unit, and we can write it simpler. These kilogram mass per second squared are also known as newtons. So newtons is actually the SI force, SI unit for force. So if you're talking about a force, you can just write that it is in newtons and not in this. But you need to know that this is what a newton is, because if you're doing like unit cancellation, you need to understand that. So newtons is actually going to be denotated as a capital N. Okay. All right. And here we have it written as a capital N right here. So it's a 98 newtons. Okay. Do I expect you to know how to find the force of something? Yes. Yes, I do. So you will be given this equation on your equation sheet, but you still need to know how to work that equation and do the math for it, which is a whole lot easier than the kinematic equations were. Alright. Our third law: for every action there is an equal and opposite reaction. So let's look at our box picture again, where we had our box with gravity. We have a 98 Newton force of gravity pulling it down. According to our third law, not only is gravity pushing down, but also the Earth is pushing up with the same force. For every action, there's an equal and opposite reaction. Okay, so that's what this means. So Earth is pushing up against the box because the box is not going down through the Earth. If it were going down through the Earth, this force wouldn't be here. Okay, but since the box doesn't go through the ground, it implies that something is keeping that box from going downward, which is the Earth. Okay. So this is our normal force. So this is the Earth pushing back against our object. It is always perpendicular to the surface. And if you remember what perpendicular is, you know that it means it's always at a right angle to the surface. Okay? You may be wondering what that means. I'll talk about what it looks like when it's on a slope here in a second. Okay? On a free body diagram, like I talked about, all of our lines, all of our force vectors are connected to the center of our object. So instead of it being like this, we're going to move that f of n number up here to connect to the center of the box. Okay? This is how it would be written if we had a box sitting here on the floor or the table. It is affected by both gravity and by the normal force, keeping it right here stationary on the floor or table or wherever flat surface it is. Okay? Now, if it's on a slope, your f of n, like I talked about, is perpendicular to the surface, meaning that it is going to be like this. So f of n is always going to be perpendicular or making a right angle with the actual surface. So as we can see, this is where the surface is, and straight line up, center of the box, for normal force is like that. Okay. In order to find f of g, we have to do that. Okay, but we also have to figure out what our angle is here, because when we're on an angle, the normal force is not opposing gravity fully, which is this vector right here. Remember, this vector is always toward the center of the Earth, which is not always perpendicular to the surface. So this is our gravitational vector, which is going to be larger than our normal force. And this is why things on a slope that is steep enough will slide down the surface, like down the slope, because gravity is still strong enough to pull it downward, down the slope. Okay? But yes, this is what it would look like here, and then you have to use some trig to find out the actual, like, force vector. Will I have you do something that complicated? Probably not. That is like college level physics right there. But just letting you know that if you have it like this, your normal force is not equal to the force of gravity. Alright, onward. When we let's look at an object in motion with an applied force. So F of A. So we know that there are two forces from gravity and the normal force. But what if we push the box on the left side, and let's say it's with 30 newtons. So if you're a person here, you're pushing the box like that. Trying to push it this way, to the left. Or sorry, to the left, to the right. You're pushing it on the left side of the box to the right. Okay? Like always, we take the arrow and we attach it to the center of the box, or the middle of the box, like all the others. This 30 Newton force is called the applied force. It's also the force that the box is going in at this point then. So it says also the force is in the right direction, because obviously we're pushing to the right. Alright. Then we have to look at what opposes that applied force, which is friction. Friction always opposes the force that's applied, as long as it is connected with something, or there's air present, because air obviously can stop things too. It's not just, a passive thing. But if we have no air, like in space, well, we don't have any friction. So when we know that friction is usually the thing that stops anything from moving. So friction, like we said, has to oppose the applied force, so that is meaning that the vector is in the opposite direction of the applied force. Say it's at 10 newtons. We attach that to the middle of the box like all the rest, so we can see that F of F points in the opposite direction. Okay? Remember, friction always opposes the forces that are applied. Okay? So we have a pretty nice diagram going here, free body diagram so far. Important, if opposing forces are equal, then it is going at a constant speed. Whereas if one force is less than another, then it is accelerating in the direction of the larger or bigger force. So if we look at this box as it is now, we can see that our force of gravity and our normal force are equal. So this means that the box isn't accelerating, meaning it's not moving in either direction, and most likely that means it's going to be sitting still. However, this does not mean that if you have forces that are equal to each other, that it's not moving. Okay? For example, if our force that's applied and our force of friction are equal to each other, this does not mean that it is stopped. It could mean that it is going at a constant speed. That constant speed could be 0, but it could also be a constant speed of like 30 kilometers per hour. We don't know because we don't have any force showing a more of a advantage against the other because they're the same. So in the case of our f of n and f of g, the box is going at a constant speed. It's just probably 0 because obviously gravity holds it down and the newtons the force of the earth is pushing it back up, so it's most likely just sitting there. However, in our case of f and f of a, we can see that we have an applied force of 30 against this 10. This means that since they're not equal, this one is going to win out because it's basically like saying 30 minus 10 is going to mean we have 20 newtons of applied force that's not challenged. And so it continues to move in that direction faster and faster. Okay? It is accelerating in that direction. Okay? Alright. When we look at hanging things or using F of t, which is our tension force, it's usually being held up by a rope or other tether, or it's being pulled. So we need a tension force that talks about that rope or tether pulling on the box or object. And so since the object is most likely suspended, if we have it like this, it's not floating up or down, right? That's not how boxes that are held on ropes work. They hang down, they don't float. So we had to assume that the sum of the tethered forces equal the force of gravity pulling it down, because otherwise it would be either going down toward the earth or it would be floating up toward the sky. So these two forces here, if you have more than one tension force, has to equal the force of gravity. Okay? And notice I have F of T1 and F of T2. Because I have two different tethers, I need to have them labeled as tension force 1 and tension force 2. Okay? So if the object is not in contact with the floor, there is no normal force. Remember this, because it's not in contact with the earth. The earth isn't pushing back on it because these tethers are holding it up. Okay, so there is no normal force in this case, so we just have F of g being pulling our object down, and we have our two tension forces holding it up. Okay? Make sense? Yay. Okay. We would attach these forces to the center of the box like we always would, and this is what it would look like as a complete, what do I want to say, free body diagram. Okay. So this is what it would look like if we had the tension forces. Alright, your turn. Label all the forces that are affecting this box under these scenarios. So we have a box sitting on the ground. You should be listing any and all forces that are affecting it. Okay? So we have a box sitting on the ground. We have a box being pushed on the ground to the left at a constant speed. We have a box is being pulled up but still on the ground. A box is pulled up into the air as it is being moved to the right at a constant speed. A box hanging by a rope and is pushed to the right at a constant speed. And a person sits on a box on the ground. Okay, and then try and make your own and quiz each other before the end of the day. Okay, so what I want you to do for the remainder of class after you've watched this whole thing, I know it's been a long, long road, but you made it. I want you to do all of these on your slideshow, on your slides, and then, like I said, quiz each other on it. Okay? Let's see. I don't think it talks about combining factors yet, so I'll stop there for now and I'll post up another one here in a second. Alright, bye physics.